In this video lesson, we'll take a look at circuits with DC sources that are extremely typical in any basic or advanced circuit. These circuits can also be used in circuits with AC sources, as you will soon find out. The voltage divider is one of the most common types of DC circuit that you will find. It's composed of a voltage source in series with two resistors. Across one of the resistor, typically one that is connected to the ground, a lead wire is attached in order to tap the voltage. In the figure, Vout is the voltage across resistor R2. We know from our previous lessons that the voltage across R2 is the same as the output voltage Vout. We can solve for the expression for Vout by determining the current through R2, since Vout is equal to the current times R2. Also, since the current is easily solved to be Vin divided by the sum of the resistances, since they are in series, then we obtain the relationship between the input voltage and the output voltage and the resistances. This expression is an ideal expression in the case when there is no load resistance at the output voltage. In the non-ideal or realistic case, any type of device has a resistive load. This is modeled as RL in the second figure. Notice that at junction A, the current splits towards R2 and RL. If RL is very much greater than R2, then most of the current is across R2. In this case, the voltage is near ideal. This is the case for the voltmeter. The voltmeter is designed to have as high load resistance as possible in order to measure the correct voltage. If RL is very much less than R2, then most of the current goes to RL and very little goes to R2. This means that the voltage across R2 also becomes very small. This is not good since very little voltage is provided to the load. We can derive an equation which involves RL. We replace all R2 in the expression with the equivalent series resistance for the parallel resistance as shown. As you can see, if R2 is much greater than RL, then R equivalent is equal to R2, which is the ideal case. On the other hand, if RL is very much greater than R2, then R equivalent is approximately equal to R sub L. A value of RL that is 10 times R2 is already an acceptable value for the ideal case. Let's consider the values given in the figure. In the ideal case, with Vin equals 10 volts, R1 and R2 are both equal to 1 kilo ohm. Vout is calculated to be 5 volts. Since this is 1 kilo ohm, and this is 1 kilo ohm, and this is 1 kilo ohm, so Vout is just 1/2 of Vin, which is where Vin is 10 volts. The current through R2 is 5 amperes. Because Vin is 10 volts, R1 plus R2 is 2 kilo ohms. In the non-ideal case, if RL is equal to 0.1 R2, then Vout is equal to 0.83 volts. The current through R2 is 0.83 amperes and through RL is 8.3 amperes. The current through R2 is smaller than the ideal 5 amperes. While the current through RL is larger, the output voltage is smaller. This is called voltage loading. The output voltage changes because of the presence of a load resistance. The load resistance pulls on some of the current and reduces the effective voltage. On the other hand, if RL is equal to 10 R2, then Vout is equal to 4.76 volts. In this case, the current through R2 is 4.76 amperes and through RL is 0.48 amperes. The current changes through R2, but not so much. the output voltage is near ideal. So the voltage across the load is appropriate. Remember that every time you apply a load to a power supply, you don't want the voltage provided by the power supply to decrease. In other words, you want as minimum voltage loading as possible. Thus, the load resistance must be at least 10 times the internal resistance of the power supply. I'll show you later how to determine the internal resistance and the load resistance. This next circuit is called the Wheatstone bridge. It's composed of 4 circuit elements, typically resistors. Each pair of circuit elements are in series, and one pair is parallel to the other. A voltage is typically measured at junctions A and B, as shown in the figure. There are 2 conditions governing this bridge, the balanced and the unbalanced. Based on the figure, Vout is equal to VA minus VB. When the output voltage is 0, the bridge is balanced. When an output voltage is present, the bridge is unbalanced. There are many applications for the Wheatstone bridge, and we'll consider one example later. For now, let's consider the case when the bridge is balanced, that is, the output voltage is 0. If you take a closer look, you have 2 voltage dividers. One voltage divider is seen through R1 and R3, and the other is seen through R2 and R4. The voltage VA is just R3 over R1 plus R3 times the input voltage, and the voltage VB is just R4 over R2 plus R4 times the input voltage. If the output voltage is 0, then the voltage across VA and VB are equal. Equating and rearranging terms, we get the expression relating all resistances to each other. You see that the ratio between the resistances to the same series are equal. That is, R1 over R3, where both resistance are in series, is equal to R2 over R4, where these resistances are also in series. Typically, one of the resistors is replaced by a potentiometer in order to balance the bridge. If the output voltage is non-zero for whatever reason, adjusting the potentiometer is performed so that the ratio of the resistances are satisfied. Let's take this example. Determine the value of R sub x in the balanced bridge as shown in this figure. The bridge is balanced, Vout is equal to 0 volt when RV is set at 1200 volts. So if the potentiometer is set at 1200 volts, then the bridge is balanced. What then is the resistance Rx? Based on this equation, Rx over Rv is equal to R2 over R4. R2 over R4 is solved to be 1.5. Thus, Rx is equal to Rv times 1.5. And since Rv is 1200 ohms, multiply that by 1.5, we get 1800 ohms. In some applications, the output voltage does not necessarily have to be 0. In one of your experiments, you are going to replace one of the resistors with a transducer. A transducer is any electronic device that converts any external variable, such as temperature or pressure, into an electrical signal. One type of transducer that converts temperature to electrical signal is a thermistor. A thermistor, short for thermal resistor, changes resistance with changes in temperature. In one of the experiments you are going to perform, you will be tasked to make an electronic thermometer by using a Wheatstone bridge and generating a calibration curve, such as the one that's shown. The change in resistance of the thermistor causes a change in the output voltage, corresponding to the change in temperature. This change may be linear or nonlinear, depending on the type of thermistor. Such type of circuit is very useful if you want to digitize your thermometer. Why do you need a Wheatstone bridge in the first place? Why not measure the voltage across the transducer directly? As in any electronic device, there is an internal resistance that you have to take into account. As you already know, this internal resistance interacts with the internal resistance of any voltmeter and causes voltage loading. This reduces the accuracy of your measurement. It also reduces the range of temperature that the bridge can measure. By instead measuring the difference in voltage across two voltage dividers, the internal resistance of the thermistor would play no role in the measurement. What the voltmeter sees is zero resistance across junctions A and B. It sees it at a zero resistance ideally because there's no voltage across the two junctions. Recall that in the voltage divider, R2 must be much less than the load resistance RL in order for the circuit to be ideal as possible. In this case, the resistance between junctions A and B is zero compared to the internal resistance of the voltmeter. The measurement of the Wheatstone bridge is therefore more accurate and the range of temperature is larger. We now move on to the last type of circuit that we are going to discuss. It's actually a generalized type of circuit in order to improve our analysis of DC and even AC circuits in general. The equivalent circuit, as shown in the figure, is composed of two circuit elements, the Thevenin equivalent voltage and the Thevenin equivalent resistance. Thevenin's theorem describes how to obtain these equivalent circuit elements. Thevenin's theorem states that the Thevenin equivalent voltage is the open circuit that is no load voltage between two specified output terminals in a circuit. The Thevenin equivalent resistance is the total resistance appearing between two specified output terminals in a circuit with all sources replaced by their internal resistances, which for an ideal voltage source is zero. In order to find the Thevenin equivalent circuit, we need to find both the Thevenin voltage and the Thevenin resistance. To find the Thevenin voltage, Thevenin's theorem states that the circuit must be open and that the load resistance is removed, such as shown. So what we're actually trying to solve for here is what is the voltage across these 2 points A and B in the figure, which is essentially what an ideal voltmeter sees. If this circuit is open at these terminals, then there's no voltage across R3. This is because there's no current passing through R3. We then end up with the Thevenin equivalent voltage to be the same as the voltage divider as shown. That is, the Thevenin voltage is equal to the voltage across R2, which is equal to R2 over R1 plus R2 times the source voltage. On the other hand, to get the Thevenin equivalent resistance, we replace the voltage source by its internal resistance, which in this case is zero, and thus it's just a wire that is shorted. We then determine the equivalent resistance at points A and B. In this case, R1 and R2 are parallel to each other. The equivalent parallel resistance is symbolized by a double bar between R1 and R2. This equivalent resistance is in series with R3. Thus, the equivalent Thevenin resistance is equal to R3 plus the equivalent resistance between R1 and R2. It's important to understand that the Thevenin equivalent circuit depends on the viewpoint. If we take a look at figure 45, we see three resistors powered by a single DC source. If we view the equivalent circuit between points A and C, we get the equivalent Thevenin voltage and resistance as shown in the middle figure. In this case, the voltage divider equation is applied across R2 and R3. Also, to get the Thevenin resistance, R2 and R3 are in series and in parallel with R1. If we view the equivalent circuit between points B and C, we then get a different expression for the equivalent Thevenin voltage and resistance. In this case, the voltage divider equation is applied across R3 only. In this case, the voltage divider equation is applied across R3 only. Thus, the Thevenin voltage is equal to R3 over the sum of the resistances times Vs. To get the Thevenin resistance, we see that R1 and R2 are in series and they are both in parallel with R3. So you get a different expression for the Thevenin resistance. In designing circuits, we also need to take into account the power utilized and dissipated by the circuit elements. Ideally, we would like to transfer all energy from the power supply to the load with as very little loss as possible. One way to do that is to apply the maximum power transfer theorem. The theorem states that for a given source voltage, maximum power is transferred from a source to a load when the load resistance is equal to the internal source resistance. This is best illustrated with an example. Consider the circuit shown with a source voltage of 10 volts and an internal resistance of 75 ohms. Everything within the shaded region is part of the power supply. The power supply provides power to the load. We can vary the load by as much as we want. In this case, from 0 ohms to 125 ohms. To solve for the power transferred to the load, we first solve for the current through the circuit. It is given by V sub S over R sub S plus R sub L. The power is then computed to be the current squared times R sub L. If we graph the power as a function of R of L, we obtain the following result. You can see that the maximum power transferred to the load resistance occurs when the load resistance is equal to the internal resistance of the source. Thus, in order to have minimal losses, you must make sure that the load resistance matches the internal resistance of the power supply. In practice, this is very hard to achieve and some compromises must be made. This last lesson for today's video will help you in analyzing circuits better and faster and will be extremely helpful with circuits having 2 or more voltage sources. The superposition theorem states that the current in any given branch of a multiple source linear circuit can be found by determining the currents in that particular branch produced by each source acting alone, with all other sources replaced by their internal resistances. The total current in a branch is again the algebraic sum of the individual source currents in that branch. Again, this is best illustrated in the next slide with an example. To solve for I2, we first replace Vs2 with the short, and then solve for the current through R2. Note that by shorting Vs2, we already see that R2 and R3 are parallel to each other. Taking the equivalent resistance and then adding to the series resistance to get RTS1, we can then solve for the current ITS1 equal to Vs1 divided by RTS1 as shown. In step D, we solve for I2S1 by first using the voltage divider equation to determine the voltage across the equivalent parallel resistance R2 and R3, or VR2 and VR3, which are equal since they are in parallel. VR2 is then equal to the equivalent resistance of the parallel circuit times ITS1. I2S1 can then be computed by dividing VR2 by R2. This results to the equation shown. The derivation of the equations from parts C to D is shown in the next slide. The current I2S2 when Vs1 is shorted is derived similarly. I invite you to derive for yourself the equations for parts F and G. The total current through R2 is then the sum of these two currents, I2S1 and I2S2. As I've previously mentioned, these types of circuits are very basic, extremely popular, and can be found in almost any type of basic and advanced circuit designs. A good grasp of these circuits and theorems is crucial in analyzing any type of circuit. Please take the time to look at a few examples in the video examples section. In next week's lesson, We'll be returning to circuits with AC sources and tackle the frequency response of circuits. We'll be using the voltage divider circuit in order to help us analyze them. See you in the next lesson.